Welcome. This is the last video in this module. So my target is to keep it less than 30 minutes. So let's see if I can do it. To so in by the end of this module, you should be able to prepare like a modeling report to communicate the modeling process and your finding. And you should be able also to describe the modeling process, including post-auditing. So that's important. Like this is just like the previous example. Yeah. Uh, we went to the site. We did a lot of investigation. We calculated like head data. We calculated concentration data. Then we developed multiple let's look here, yeah, like, then we develop multiple conceptual models. That's a good review for this module. Then we will said, okay, we will turn this conceptual model to a numerical model using mudflow. We set up our mudflow model. We calibrated our mudflow model. We did this for multiple conceptual model. So we calibrated our mudflow model, and after we calibrated our mudflow model, now we have a calibrated model. We started to do our application. So what was our application? Our application was to capture these plumes and not get them like escape the our site. So how we do this? We did like some particle and we tried to capture all these particles, and then after we captured all these particles and we found the design, we realized that we have a problem because we are capturing all these particles. We need to pump, I don't know, 660 meter cube per day, and this is 660 meter cube of contaminated water each day. What are we going to do with this water? We need to treat it. So in order to treat it, we need to know the load, like what is the contamination load, like the concentration. And to do this, we need to run like a transport model. So we run our transport model. And then after our transport model, now we know the load, yeah, the contamination load. Then what do we do with this? Then giving this load, we design our water treatment unit. And now we have a water treatment unit, like, and this is for like 30 year. So we do like, what do we do? Like, we need to calculate the cost for like over the like design period of 30 year. How do you do this? Like you do like engineering economy, you account for time value of money, and then you get a figure. So now you have a design, you have a cost, you have a treatment unit, and so on and so forth. And now you need to report this to your client. Are you done? No, you're not done, because after you do this, they will what they will do, they will implement this design that you suggested, and then you should be doing some post auditing. See, is this design working or not working? If it's working, it's fine. If it's not working, now, what part of it that's not working that we need to improve? Okay, so that's like the implementation and post auditing. Like after you report your finding and you give them the designs and they need to implement. So that's what we will be learning in this lesson. Let's start with the modeling report. So now you have a modeling results. After you have your modeling results, what do? You prepare figure and write your report. No, you should, before you do this, you should check for errors. Check, like, for example, for your input, data input error. So let's see, that's like, that's your model here. Yeah. Like Mudflow, that would be the list file of your Mudflow. Make sure that like your input data does not has errors. So just scan through this and make sure that like you don't have like any errors in your input data. Water and mass balance error. The model will run and then you will get like a mass balance. Let me show you like example of the mass balance. So mass balance like will tell you like your input should be equal to your output plus or minus like any changes in storage. In your case here, this is like a steady state model, so your input should be equal to your output. So here, like the input is coming from recharge, that's like your only input. Your output, like, so water will be recharged and will be output through the river. And you see here the input is almost the same as output. The discrepancy is zero. So now you check the mass balance. So that's like another thing you check. If this mass balance didn't match, this means that you have numerical errors. Like your numerical solution has some error. Uh, Check computed variable for reasonability. Like, is this drawdown reasonable? Is this travel time reasonable? Is this velocity reasonable? Is this concentration? Is this fluxes? You can even perform hand calculation. If it doesn't sound reasonable, you can perform hand calculation and just make sure that whatever you are getting, these are like the same order of magnitude. Check also the assumption. Like we had assumptions, yeah. Uh, are our assumption correct? Like for example, like one of our assumption. Let me just show you like what we did before in your homework. Like one of the assumption we had. Uh, oops, where is that? Why is it not showing here? Yeah. So oops, one of the assumption here, like see this B3. When you block recharge from here, our assumption that like this is not recharged and B4, that's where we will get our maximum drawdown because that's where we are blocking recharge. So these are not recharges. So that's our assumption. And then we run our model and then we see is our assumption true? Do we have a good understanding of this system? Really like we get like the most of the drawdown is in B3 and B4 or not? Yeah. So that's like also like something you check before uh, you start like writing your model, check model assumption for consistency of the results. And another thing, rework results uh, for presentation to stakeholders. So the results, the way you get them, that could make sense to you. You could understand it, but that does not necessarily mean that they will make sense to your client or your stakeholders. So represent or present the result or rework on your result and try to animate them, try to represent them, try to show them in a way that will make more sense to your stakeholder. Yeah. Then and then you will like uh, then you can start writing your report. Like for example, let me show you. Like this, is what I generally do. Like before I even start writing, I collect all the figures. So like see here, that's exactly before I write any report or any paper. What I do, I collect all the figures. So I want to show this figure. 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 I want to show this. Sometimes I even annotate them, put like a title to it. And then now I have all the figure and then I start writing my modeling report. Typically, your model report will include something like this, yeah? It will include like a cover page or like a cover page with the title, like project title and so on, executive summary or like an abstract, introduction, then like the hydrological setting and the conceptual model, like what are the hydrological setting, like what is the recharge, what are the rivers in the area or ponds in the area, what are the geology and the hydrogeology of the area, rainfall, land use, and land cover in the area. So you provide this hydrological setting. System property, like your hydraulic conductivity value. Your observation, for example, like you have this is my observation. Well, system property could also include pumping, like how much you're pumping, yeah, and the pumping rate. Observations. These are my observation well, and these are my observation point. Conceptual model. Giving all this information, I develop like this conceptual model or multiple conceptual model. Then your numerical model, like you can put like the governing equation and the code. Usually we don't put the governing equation. In your specific example, I want you to do this. Typically we don't do this, but I want you to do this because this is part of what I want you to learn. Yeah. Then you put like your design, your model execution, your model calibration, forecasting, simulation, and uncertainty analysis. Then you discuss like your results. And after you discuss your results, you discuss like your model assumption, simplification, and limitation. You discuss your model limitation. Like now, this is the results, but this is my uncertainty. This is what we know, but like take this discussion and take this giving these like limitation, and then you put some summary and conclusion. And then here you share your data, you put an open data statement, like if you sharing like where can like you the user finds this model, download it and work with it, like reference list and any appendices. So for your project, uh, I put a link here. So that's like your modeling report. It looks something very similar to this. You need like to have like a title and abstract, an introduction, and I'm providing you details of what I'm expecting to find in each of these sections. Hydrological setting, the numerical model, the model applications, the conclusion and limitation. So I want you also to talk about the model limitation and cited references. Yeah. So you can check this, and you can check also the rubric here. So you can also read this rubric because these are easy point, and uh, that's like that's also one thing, one skill, like in addition like to your technical skill, soft skill are usually more important than these like skills like running a model or something like this, because these soft skill like technical writing, that will that's how you communicate your results. So you should be able to communicate your results in a good way. Okay, so model limitations. That's what we already talked about this, but let me just talk about it again, like data quality and quantity. Sometimes you don't have enough data, or sometimes your data could have an error. Uh, in certain area, models does not exist or inadequate. Like uh, so in certain areas, like sometimes you will not be able to develop like this numerical model, because sometimes this system is like too complex and we still don't understand it, or inadequate mathematical solution techniques or numerical techniques for this simple, or insufficient computer power. So that's also some of the limitations. So if you are facing any of this limitation, you should also describe this. Yeah. Model accessibility. Sometimes, for example, like many, we couldn't like the accessibility to Mudflow was not easy because you need to know a programming language to use it. But now uh, GMS developed like a graphical user interface, for example. This is just one of them. But sometimes you don't have enough funds to get this license, yeah. So, but now USGS developed ModMuse, so that make accessibility to this ModFlow model easier. But some other model, like hydrogeosphere, for example, like or fee flow, this requires license. The model itself, like the flow model or the transport model itself, is not free. You need to get like license for it. And then like model documentation and uh, trained experts. Sometimes like you will find like an existing model that you want to use, but the model documentation might not provide like the amount of details that you need to like reuse these models. So make sure that in the model like when you document your model, make sure to mention all this limitation, and make sure to make your model reusable. Yeah. And then like other model limitation, yes, is that like trained expert, like these models they like these models, they requires a lot of expertise. I just give you like very simple example, but real world examples, they require like a lot of expertise. That's why modelers, they get paid more than they get paid like a high salary, because it's a very technical job and it requires a lot of expertise. So you need like this model. Like another limitation of this numerical model is that they are expensive to develop and they require trained expertise. Like if you want like I will show you like like some of this USGS model, and you want to the USGS and ask them to develop one of these models for you, they will charge you at least $1 million to develop one of these groundwater models for you. And then model credibility, again, the model credibility would be as good as your input data. Like if you have a high quality input data, and uh, then you will have then your model would be more credible. But in addition to the input data, also like how you address your uncertainty and how you communicate this uncertainty to your users. The more you are transparent about your uncertainty and the limitation of your model and the limitation of your data, the more that will increase your credibility. Now, giving all this information, I want to tell you that decision making is not solely based on prediction or screening done with models. There are other considerations that could be taken into account. Like, so model only support decision. It provide like information, but that's not how decision is made. And I give you an example, like the trade-off between like spring discharge and pumping. What model will do, it will provide you this curve, this trade-off curve. Like if you pump it that much, that's how much your spring discharge will decrease. But uh, but decision could be like where to pump, like how much will pump. That could be based on societal preferences and this like by engagement, like engaging your stakeholder, and where different like actors will engage in discussion and decide on these things based on the information that's provided by the model. So that's why we call it like decision support. Like this model only support decision. Yeah. So here, these are modeling reports. So these are example of some modeling reports. Uh, this one is in Hawaii. This one is in Florida. I use both of them. Uh, let me just try to get this one. Yeah, let me try. Let's just look at it together. I usually tell the student, please read any of these one, and they don't read it. I mean, I don't know. Most probably they don't read it. So, uh, I will just want to go with it with you. Yeah, just very quickly. Yeah, you do it very quickly. So here it start with like a cover page that has like the title numerical simulation of the effect of low permeability valley field barriers and read distribution of groundwater withdrawal in Pearl Harbor, Oahu, Hawaii. So here, just low permeability valley field barrier. These are like some low permeability zone that will prevent saltwater intrusions that's coming from the ocean. So if you have like some here low permeability zone, that will act as a barrier for saltwater intrusion. And then here we want to redistribute groundwater pumping, like withdrawal, in order to like do some mitigation for this thing. So how, like, see, you see here, this is like the cover page, like table of content, and so if you want to the USGS to develop a model like this for you and create this modeling report, that would be at least like $1 million, at least, yeah. And then here start with an abstract that describes a problem, and then the introduction here start with the setting. It probably will talk about the geography and the history of this region. Like, let's see here, what do we have? So see this map here, state of Hawaii aquifer management system. So here it talk about like the aquifer management system in the state of Hawaii. See this figure, mean annual rainfall. So here it like a map of the rainfall. Remember, we talked about this, yeah. We talked about like, and then like we talk, and then here about land use, what are different land use like sugarcane cultivations and pineapple cultivation. And you see here maps for the 1919 to 1910s. It was mainly, what was they mainly doing? It was like pineapple, little bit of pineapple, but mainly like sugarcane. And then it shows you how this is changing over time. And that will create like, why is this information is relevant? Because that's how you create like stress on the water. And now here, starting from this, where drip irrigation started to appear, and then by the end here, like in this late period, you mainly find like no sugar cane and drip irrigated like sugar cane. No sugar cane is only pineapple irrigation. Yeah, like only pineapples that was cultivated, and that will mean that like your aquifer will start to recover, and you will not have big drawdown because you're not doing sugar cane, which is water intensive. And then you talk about the climate. So climate, that's like rainfall. And then you talk about the geology. And so here that would be like rainfall data. And here that would be the geological information of your area. So it will talk about like different like geological area, which will have different hydraulic conductivity property. Yeah. So different geological area, which have like different hydraulic conductivity property. But you see like here, like again, like these details are like what I want to show you here is the, so here like talking about different rock types and the how these different rock types and their geological modification, and that's part of the purpose of the model. The purpose of the model is to understand the impact of this low permeability areas, and then to understand this you need to describe it to the reader, to tell him what are these low permeability area, and then you describe like the hydraulic conductivity here. And then here, remember like storage, like if you remember, like you see something here, you've seen this equation before, like storage coefficient and specific yield. And then here they talk about the valley field barriers and this different conceptualization for this valley field barrier. So all here are like different conceptualization for this valley field barrier. And then starting from here, this is like the observation data, some of the observation data that was used for model calibration. Then we here is talk about recharge, how recharge was like estimated, and the groundwater groundwater flow direction. So a map showing like what are the groundwater flow direction. This is in the subsurface, a conceptualization for the subsurface. You have a freshwater lens, you have brackish water here, you have salt water here. So you see like a lot of very interesting and figures. And then, so basically, this is like the head data that was measured. So here is basically telling you some head data that was measured, showing it to you. And here will be what is this one? This is a model grid. It will show you like the model grid and the boundary conditions. So you see here, this is the model. Oops. Here you see that's the model grid. These are different boundary conditions described here. Uh, so I, in your final report, I expect you to do a report like this. Yes? No, I don't. But eventually, yes. Eventually, like as you move on with your career, I expect you to do like a report like this. Because some of you will be working in like one of the students like who took this course, she now working as a groundwater modeler in South Florida Water Management District, for example. And she will be producing reports like this. And that's why I'm showing this to you. Yeah. Not for this class project, but and see here like describing like water properties, aquifer properties, and then now here see this figure, it shows you simulated versus observed, like we talked about this before, like simulated data versus observed data. Here this is simulated data versus observed data for the spring. So this one was for the head, this one for the spring. And you see like you can, it's not perfect, but again, like why this is not perfect, because sometimes like measuring a spring discharge like is not accurate. So this data, like your observation data, might not be very accurate, and then so you have error here and you have also error here. But like see here is working, but overall I think it's a very good fit. Yeah, to be able to fit something like spring discharge. But anyway, so here this is again like head, like simulated head versus observed head are plotted, and and so on and so forth. And then like you keep going with your model until here they tested like at the end, the purpose was to test like a different water redistribution scenario. So I want to show you here. Yeah, and then now they do like tested 6 scenario to show like what, or like 7 scenario to show what is the best water distribution giving like this very field, like how we can redistribute the use of water so that we take advantage of these natural barriers. Yeah. And then this would be the project like summary where you put like, and then see here, this is the model limitation. Hopefully, if you have time, please read this. That is an excellent example of a model limitation. Yeah. And then a summary of like the work and the finding and the recommendation. And then the reference cited. And then after the reference cited, some appendix where you put like the monthly groundwater withdrawal during, so this is like the pumping data like from this period to this period and so on and so forth. Yeah. So this is, I showed you this example. Try to look at this example. I'm trying to keep this less than 30 minutes, so I need to move forward. Yeah. I have a few minutes. Yeah. So implementing and post auditing. So we talked about this. Yeah. Uh, so this is the modeling process, and then after the modeling process comes a management process. Like, so they will take a management decision, they will implement this decision, that will be implemented into the environment, and then after you do this, like you will see like where you will able to identify a problem. If everything is working fine, that's fine. If not, then you can see like if you identify the problem, like why this problem is there. Is it because like we made a wrong management decision, or there was something wrong with our modeling process? And then if it's something wrong with our modeling process, we can go like to here, to here, to here, or to here. And then like from problem identification to water management, this should be also public opinion, stakeholders should be involved, with competent authority and government. So it should be done in with participation. Like participation is a very important component for this. So here, this is just like a summary figure. So here, like this is your modeling process where you have your surface water, groundwater modeling system. You have groundwater dependent ecosystem and human activity. Human activity like sugarcane farming versus organic farming versus pineapple farming. Yeah. And then you need to acknowledge your uncertainty, and then that need to be done with a democratic process, like through a participatory process. So you can check this if you want to read more about this. You can check it here. And so, in conclusion, the models, they don't replace hydrological analysis. They just improve the hydrological analysis, but you need to do like your hydrological analysis. You need to interpret your data. Uh, the effectiveness of the model depends on the quality of the data and quality of the modeling process, including accounting for uncertainty. Modeling is just one tool that the technical expert has available to assist in decision making. So modeling is just one tool. Some places you cannot afford to make these models, so you can just make some simple calculation. Yeah? Or some places you don't even need a model. You can just collect some data, and from this data you can make your decision. So modeling is just one tool, and you need to assess like if modeling is the most feasible tool to use or not. Yeah? And generally, best decisions that would be based on like integrated use of resources, and here like uh, participation, and you acknowledge the uncertainty, like epistemic like humbleness. You acknowledge that your knowledge is not complete and try to be transparent about it. So I think that's it for this module, and like see you in the next